In this lecture, we will learn what trees are. Nodes of a tree are connected by edges. There are several terms that we need to understand in order to work with trees. Root, the top node of a tree. There's only one root per tree, and only one path from the root to any given node. Leaf, a leaf is a node that has no children. Visiting, checking a value of a node when control is on the node. Levels, the generation of a node. There are three main rules that all trees follow in order to be a tree. Starting from any node, any other node in the tree can be reached. There are no cycles, and the number of edges is one less than the number of nodes. Let's learn about the different types of trees. A binary tree is where each node can have a maximum of 2 children, and we have the benefit of ordered arrays for searching and linked lists for inserting and deleting. A complete binary tree is a binary tree in which every level of the tree is fully filled, but perhaps not the last level, and the last level is filled left to right. A full binary tree means that every node has either 0 or 2 children, and no nodes have only 1 child. A full and complete binary tree is both full and complete. All leaf nodes will be at the same level, and this level has the maximum number of nodes, and it must have exactly 2 to the k-1 nodes, where k is the number of levels. A binary search tree means that a node's left child must have a value less than the parent's value, and the node's right child must have a greater value than the parent's value. A heap is a type of tree where insertion always goes from top to bottom, left to right. If it is out of order, swap it with the parent and keep going up the heap with this process. To implement a heap, we can store an array. An AVL tree is a balanced binary search tree. Balanced means to check the height of the left and right subtrees, and the difference should be no more than 1. To balance itself, it can perform the following operations: left rotation, left-right rotation, and right-left rotation. AVL trees are binary search trees. They maintain balance through rotations. By ensuring that all node subtrees' heights differ by no more than 1 at most, AVL trees guarantee that insertions, deletions, and searches will always have a runtime of 0 log n, regardless of the order of insertions into the tree. A splay tree brings the most recently accessed item to the root of the tree, and makes the recently searched item accessible in constant time. It is much faster for lookups. It is easier to implement than AVL trees, since rotation logic is much easier. And a splay tree reshapes itself based on lookups. A ternary tree is a tree with up to 3 children. With a red-black tree, in addition to its data and left and right children, the nodes of a red-black tree contain a color, either red or black. Nil nodes as leaves instead of null values. Every node is colored either red or black. Every nil node is black. If a node is red, then both of its children are black. Every path from a node to a descendant leaf contains the same number of black nodes. Red-black trees are self-balancing, and when insertion or deletion happens, nodes are rotated and recolored. A universal value tree is a tree whose values are all the same. A trie is a type of tree. It stores characters that make up a word. It's helpful on find all the word problems. With this type of tree, we don't look up each prefix from the root. Rather, we build on past calls. In the next lecture, we will learn how to create a tree using Python code.